All right, let's talk gear trains. So typically speaking, if we want to have a relatively high gear ratio, then we got two options. We can use a really small gear and a really large gear, or we can combine stuff. So we can use a combination of uh, different gears set on different shafts that allow us to uh, basically kind of multiply together the gear ratios between those relative ones, and that would allow us to uh, essentially increase our gear ratio without using a massive freaking gearbox. So, for example, another thing is if you use an even number of stages, then your rotation direction maintains the same, goes the same way as well. So here's an example that we got here. We also got you know, three stages here. This one starts off with the input here is a bevel gear, connects to bevel gear, and then we got a number of helical gears that connect to it. So again, each stage will have its own pinion and its own gear as well. So as well, this allows us to do things like have variable speed transmissions. So for example, here we've got uh, a here we got the gear selector. So basically, this gear selector connects to clutches here. Those clutches connect to the shaft. It's driving our so connect our shaft. So those connect to the output. So by selectively connecting each of these clutches to uh, one of these gears, we're retaining different gear ratios based upon the input, and that's based upon basically just the relative size, uh, the relative combination of the different gear ratios for um, this first set, and then this set or this set or this set right here. This one's the reverse one. That's because that has that idler gear in the middle. So the idler gear not only changes the gear ratio, it also switches the direction. Technically speaking, I think we should have there's a negative sign there. So the gear ratio in general, when we're talking about when we're talking the gear ratio, we're talking about the relative rotational speed between the input shaft and the output shaft. So the input shaft divided by the output shaft, so this A shaft here and this C shaft here. So basically, that can be found based upon combining the fact that when we have this input coming in, it's going to get transformed based upon this combination of gears into an intermediate input here, an intermediate rotational speed, and then that rotational speed gets transformed once again into the output speed. So that's kind of based on the exact rotational speed of that intermediate shaft cancels out in terms of the inputs and outputs, and it's just based upon a combination of the ratios of of either the diameters of the relative gears. So again, we got gear 1 and gear 2, so gear 1 and gear 2, and then pinion 1 and pinion 2, so pinion 1 and pinion 2, or the number of gears, number of teeth on those gears, gear 1 and gear 2, and pinion 1 and pinion 2. Again, keeping in mind that the pitch kind of at each of these meshes needs to be constant, so those ratios are going to those two ratios are going to end up being the same. Now when I say the pitch needs to be constant, that's for each pair of gears. We do not have to have the same pitch for between pinion 1 and pinion and gear 1 as we have for pinion 2 and gear 2. Those can be different. And yeah, so here, for example, if we have if we are trying to design something that will have an input of 3600 RPM and an output of 400 RPM, or not T, and we have a center line distance kind of like between the two shafts of 4 inches, then essentially what we that allows us to figure out what we'd need there. So again, first off, we have and in this case we want the input shaft and the output shaft to be parallel to be coincident with one another, concentric with one another, so that'll also come into play. We don't necessarily always need to have that be the case, but in that case it'll be an additional constraint. So if we want that to occur, then basically what we're going to need is we are going to need to have the same gear ratios for these two sets, basically. So otherwise we'd end up with something that had slightly different centerline distances. So if we wanted to do that, 36 to 400, that'll give us that's 9. It's a gear ratio of 9. So what we want then, scrolling up here, we know that our input rotational speed divided by our input output, divided by our what am I trying to say here? Divided by our output speed is 9. So that means that this relationship needs to be true. Now, if we're using identical gears for the pinions and for the gears, so if P1 is identical to P2 and if G1 is identical to G2, then this relationship here ends up being NG squared divided by NP squared is equal to our gear ratio, so that's going to be 9. 9. So I take the square root of that, and we're left with, if we take the square root of that, we're left with a gear ratio of 3 between the gear and number of teeth of the gear and the number of teeth of the pinion. And that'll also give us our ratio of the diameters. So the diameter of the gear divided by the diameter of the pinion needs to be equal to 3. And then we're left with the fact that we know that the offset between the two needs to be 4 inches. So therefore our radius of the gear plus the radius of the pinion needs to be equal to 4. So obviously if the diameter of the gear is 3 times the diameter of the pinion, then the radius of the gear needs to be 3 times the radius of the pinion. So we can plug that relationship in there. So we'd be left with 3RP plus RP is equal to 4 inches. So therefore the radius of our pinion needs to be 1 inch. the radius of our gear needs to be 3 inches. So the diameter of our gear needs to be what am I trying to say? 6 inches. The diameter of our pinion needs to be 2 inches. So straight gear trains like that are fairly straightforward. We've also got planetary gear trains. So these are often used. You'll see them in automatic transmissions at the very least, fairly often. The fun thing about planetary gears is that it allows you to kind of change your gear ratio by selectively kind of engaging clutches and engaging brakes on the gears, on components thereof. So at this point, I posted a couple videos in the a couple note videos in Moodle. So go ahead and watch those, and I'll give you a second there. And yeah, so yeah, the basics is that by selectively stopping the rotation of some of these, we're able to pick our gear ratio. So when we're doing that, we got the 3 different things that we could be worried about. We could be worried about the rotation of the sun, the rotation of the ring, and the rotation of the arm and carrier. And if we have, essentially, if we want there to be, if we're applying an input, if we want there to be some sort of output, we need to apply 2 inputs. Because basically, if we just apply an input to the sun or the ring or the arm, and we don't constrain, if we don't constrain at least one other input, then all it does is spin. It spins uselessly in neutral, and that doesn't really help anyone out, now does it? So, well, that having been said, the fact that neutral exists is useful, because oftentimes you do want to put your car in neutral, or you do want to not have to completely shut off the engine, even if you want to have not be moving anything at that point. So anyways, but if we are trying to achieve some sort of transfer power, if we are applying our rotation, our power to the sun, and we fix the ring, then the output is going to be the arm. If we fix the arm, then the output is going to be the ring. If we're applying the rotation to the ring and we fix the sun, then we got the output to the arm. And if we fix the arm, then we got the output to the sun. If we apply the rotation to the arm and we fix the sun, I'm pretty sure you can fill in the rest. Ring, sun. So we got the site here. Let me just navigate to it real quick. Okay, so this site here allows us to pick, it allows us to select certain different numbers of teeth, and it allows you to specify the input speeds. You can have 2 different input speeds, and then you'll have a separate output speed. But you select which one you're solving for. So you're either solving for the sun gear, you're solving for the planets and carrier, you're solving for the ring gear. I'll be completely frank, I'm not sure why the operation of the site isn't showing up properly on my screen recording software. Just go to it and play around with it. But this is going to allow you to basically determine kind of how a relatively simple planetary gear set would result. So again, like I said, typically speaking, you're going to be locking one of your inputs. That having been said, you can actually be supplying power to two inputs at once and get a reaction based upon that. But if we go back, we're going to need to use a bit more, for more complicated gears, we are going to need to use a bit kind of a better method. So I'm going to use a tabular method that's outlined in Norton's textbook. So what you do is you set up a table with a column for the rotational speeds of the gear, the arm, the relative rotation, and the relative rotation between the gear and the arm. So that's just saying that the gears, any gear, and here we're talking gear like the ring gear, the planet gear, the sun gear, so on and so forth. Any of them will be rotating at a particular speed, and the arm will be rotating at a particular speed, and and then there will be some sort of relative rotation between the two. Now, when you apply, and then we have a gear ratio column, uh, and just due to the fact that you get the carrier rotating around, and that's holding, that's applying that relative rotation between the planets and either the sun or the ring. The gear ratios that we have apply to the speed of it's applied to the relative rotational speed of the gears relative to the arm. So basically that third column is what you apply the gear ratio to. And again, just keep in mind, gear ratios are negative if they're both external gears. Whereas if you have the ring gear and one of the sun gears, then then it's a positive one. They're rotating in the same direction. So here, let's see an example here. Well, just look at this. So if we were, I'll just, if we were to have the sun fixed, so let's just call that S. The sun's going to be S. The sun's connected to the rings. Sorry, the sun's connected to the planets, and then we got the ring. So the rotational speed of the sun is 0. And then that means that the rotational speed of the arm is going to be our input. So in, it's omega in. So our rotational speed, the relative rotational speed of the gear and the of the sun gear relative to the rotational speed of the arm just needs to be negative W in. Then we got this gear ratio here. So that's the gear ratio between the sun and the planets. That's going to be negative, and we're going from 1 to we're basically going on down. So basically we're going to have N S divided by N P. And then from there, our W in, that's still fixed for all of those because our input is the arm. Then we know that the relative rotational speed of the planets, so the rotational speed of the planets relative to the arm is going to be based upon this this gear ratio here. So that'll be W in minus, W in times ns over np. So we've got that. We can figure out what the rotational speed of the planets are, but we don't really care all that much, to be honest, at this point. But from there we can go to the rotational speed of the ring. So the rotational speed of the ring is our output, so that's the one we're worried about. If the sun's fixed, we're worried about the rotational speed of the ring if the arm's the input. So the gear ratio there is going to be, again, the speed of the the speed the speed of the input divided by the speed of the output is going to be equal to the n of the planets divided by the n of the ring, and that those two things multiply. So this value here, the gear ratio, multiplied by the relative rotational speed of the gear and of the planets in the arm. That'll give us W in times, we're going to have NS NP divided by NP NR. So it's going to be NS over NR when the NP's cancel out. So then for actual output, W in plus W in times NS over NR. So that'll be 1 plus NS over NR W in. So we can compare that to, let's set that up in our calculator. So we are working with here, we're trying to solve for the ring gear. We're setting the sun speed to 0, setting the carrier speed to 1 here, and it's giving us an output of 1.275. Whereas based upon the calculations that we just did, let's see, so our relative teeth numbers here. Set up our relative teeth numbers here. So we expect the output to be 1 plus NS, number of teeth of the sun, 28, divided by NR, 102, times the rotational speed. I had it 1. All right, so 1.2745. They rounded up to the 45. So yeah, that matches. Good. So like I said, we can use the calculator for relatively simple ones. Problem is that it's not always that simple. So what do we do if we have, say, something like this? So here we've got a setup where we've got a couple gears going on here. So we got the ring connected to a planet, but the planet this planet here doesn't connect directly to the sun. It's on a separate shaft here that also it's on a separate shaft. That shaft rotates at the same speed as the planet, but it's got a different number of gear teeth here. So basically, it's a compound version of a planetary gear. So I can't just plug that into the calculator because the calculator is not that bright. So we can still use the tabular method to determine what's going on here. So scroll down a little bit here. So in this case, we want to figure out what the gear ratio is, and the output RPM is if we have the input shaft rotating at 200 RPM. So the input shaft is here. That's our input shaft, so that's the sun. So we'll start off with the sun. Rotational speed of the sun is 2000 RPM. And we also know that the brake is activated. So if the brake is activated, then we know that the ring is not rotating at all. So if the ring's not rotating at all, that's N1, so that's 0. So what we can do here, and what we're trying to find out here is this output here, that's connected directly to the arm. So the arms, the rotational speed of the arm is our output. So just fill that in here. And then we got our gear ratios. So again, just kind of going like this. We know that our gear ratio for N2 to N3, that is going to result in, let's see, so the gear ratio for N2 to N3, that's 25 divided by 45. Sorry, that's negative 25 divided by 45 because it is an external gear to an external gear. Our gear ratio from N3 to N1, that's 0. Those aren't actually gears, right? Sorry, it's 1 because those are in the same shaft. So the rotational speed of the rotational speed of those gears are the same, and obviously also their relative rotational speed relative to the gear is also the same. So the other one that we can fill in here is our N4 to N1. So we got the 25 divided by 105. So going from here to here, going from up here to over here. Again, no negative sign there because one of those is an internal gear. So we can solve for a few of these things here. So let's start at the bottom here and kind of work our way up. So we know that the N1, this N1 here, the sun here is locked, so its rotational speed is 0. So therefore our W gear relative to arm, that needs to be equal to negative W out. So if we go up from here to here, then what we need to do is we need to divide by that gear ratio. If we're going down, then we're multiplying. If we're going up, we're dividing. So negative W out divided by 1 divided by 25 over 105. That gives us negative 4.2 W out. So again, we keep our negative sign there from the original W out. Just copy that over here. And then we can work up to our other one. So again, going from the negative 4.2 W out, we need to divide by this gear ratio. So negative 4.2 divided by negative 25 divided by 45. So that'll give us a 7.56 W out. So then we just need to solve for the fact that our if we just want input divided by output, our input W in is equal to W out plus 7.86 W out. So therefore our gear ratio is just going to be 1 over the ratio, sorry, other way around. Our W in divided by W out is equal to take this, factor out the W outs, and that's equal to 8.56. So that's our gear ratio. So the rotational speed of the output shaft will just be 2000 divided by that. So 233.6 RPM. Okay, so sometimes those get a bit complicated, so we'll have a look at an example of a Buick Dynaflow transmission. So what we have here is a set of gears and brakes and clutches. So we got the input here. The input is connected directly to this Sun Gear 2. The input shaft also has a clutch that can be engaged. And if that clutch is engaged, then this Sun Gear 6 also rotates at the same rotational speed as 2. The Sun Gear 6, however, can also be stopped from rotating instead if this brake B1 is applied. The Sun Gear 2 is connected to this Planet Gear 3. Planet Gear 3 is connected to this Planet Gear 4. Both of them are on this carrier here, carrier arm. Not really an arm, it's a shell basically, but that's the output. And then 4 is connected to 6, the Sun 6, and it's connected to the Ring 5. So Ring 5 can be left to rotate as needed, or it can be locked by applying the brake at B2. So let me just kind of erase my lines here, and we'll kind of look at what happens here. So if we have want to put things in a low gear, we do that by blocking the rotation of the Sun 6, applying the brake at B1. So the input again is always going to be the Sun 2, or at least always going to be at least the Sun 2. It could also be the Sun 6. And then again, the output is our arm 5 that's connected to our 2 planets. So if we block off the rotation here, then this thing can't rotate at all. And we are still getting rotation of our of our Sun here too. So again, 6 not rotating, 2 is rotating. When 2 is rotating, then that means that 3 needs to be rotating as well. So 3 is going to be rotating like this, which means that it's meshed with 4. 4 needs to be rotating. So 4 needs to be rotating like this in this direction. But 6 is not moving. So if 4 is rotating but 6 is not moving, then that means that 4 needs to be rotating by also crawling along this way, which is what achieves the rotation. And as it crawls along this way, 3 and 4 are both connected to the arm, or the output, and that drags it along that way. So that is how we attain our gear reduction there. So that's a low gear. Another configuration that we're looking at is high gear. So this is when we're going to be having Sun 2 and 6 both as the input by engaging that clutch. So when we do that, just let me erase these lines here. So if we do that, we've got, this clutch engages, B1 disengages, obviously. So if we do that, then these two things are both rotating at the same speed. So if those two things are rotating at the same speed, then we've got this is rotating this way, this is rotating this way. Then that means that we're going to get this thing rotating this way, and this thing wanting to rotate that way. So as a result, basically what we're going to see here is that those two, the 3 and 4 are going to want to rotate against one another, but they can't. They can't do that. So instead of attaining this rotation by having 3 and 4 rotate, all this rotation just needs to be done by having 7 rotate at the exact same speed as the input. So here we got, so that locks those 3 planets against one another, and then basically connects. That means we're connecting our arm directly to the input. And then we got reverse gear. So if we're going to leave here, we're going to use the Sun 2 as the input. Again, we always use Sun 2 as the input. We're going to leave 6 free. So we're not going to cause it to stop, and we're not going to cause it to be locked with the clutch. It's going to be free to rotate, but the ring's going to be rotated. We're going to be activating that B2. So that B2 is activated. So our B2 is activated, our B1 and our clutch are free, so this thing's free to spin as needed. So basically, we're going to have input coming in this way, rotating. Oh, here, I'll go to this one. So we got input coming in this way, and this thing's going to want to rotate this way, which means that this thing's going to want to rotate this way, and this thing's locked. So if this thing wants to rotate this way, counterclockwise, and the ring here is locked, then the only way that it can accomplish that is by crawling in this direction. So we're reversing the rotation speed by leaving our Sun 6 free and locking ring 5 with our brake. So we got we've got the relative the relative the relative number of teeth listed here, and those would result in basically the different gear ratios. So in general, if we want, so what we're generally looking for, reduction is when you want your output speed lower than input. We're driving up the torque. Overdrive is when we want higher speed than input, so that'll obviously reduce the torque. Reverse, switching our directions. Neutral, if you don't hold anything, then no torque gets transmitted and everything spins uselessly. And then direct drive is basically locking the input to the output via these clutches and brakes. So some examples of ways you could accomplish this.